Somewhere in this galaxy right now, a signal is crossing empty space that will never reach anyone at all. Not because it is too faint, not because something is blocking it, because the thing it is racing toward is retreating from it faster than light itself can travel. That single fact, quietly buried inside the mathematics of an expanding universe, is enough to end the search for company among the stars before it even begins. We assume that if life is common, contact is simply a matter of time. Build a bigger telescope. Wait a few more centuries. Eventually somebody says hello, and somebody else says hello back. This is why that assumption quietly falls apart the moment you look at the numbers. Seriously. Because the same forces that scatter billions of habitable worlds across our galaxy also wrap each one of them in a kind of isolation that no amount of patience, ambition, or cleverness can undo. Before we begin, be sure to like the video and subscribe for more journeys into the cosmos. Now, take a deep breath and let's begin. Picture the moment before that signal was ever sent. A civilization somewhere in the galaxy builds its first radio transmitter, points it at the sky out of nothing more than curiosity and hope, and sends a message outward with no idea whether anyone will ever hear it. That is, in fact, exactly what happened here on Earth, only a little over a century ago, when the first deliberate radio transmissions began leaking outward from our own planet into the surrounding darkness. Every single one of those transmissions is still traveling right now, expanding outward as a thin shell of radio waves roughly 100 light-years thick, carrying the earliest news broadcasts, the earliest music, the earliest accidental proof that something intelligent lives here, out into a galaxy 100,000 light-years across. That shell of signals has, by the standards of the galaxy, barely left our own front porch. It has not yet reached even a small fraction of the stars closest to us, let alone the thousands of light-years separating us from wherever the nearest other civilization might actually exist. Start with a number that sounds encouraging. Our galaxy holds somewhere around 400 billion stars. Some are ancient, dim, and patient, burning so slowly that they will still be shining long after our own star has gone quiet. Others are young, hot, and reckless, living fast and finishing their nuclear fuel in a geological blink. Between those extremes sit an enormous number of perfectly ordinary stars, and around ordinary stars, planets form as a matter of routine, not as a rare accident. For a long stretch of the last century, this was simply an assumption. Nobody had ever confirmed a planet orbiting another sun. That changed once space telescopes were built specifically to watch for it. One of them stared at a single patch of sky for years, tracking the brightness of well over 100,000 stars at once, waiting for the tiniest possible dimming, the shadow cast by a small world crossing in front of its star. The dimming these instruments were hunting for is subtle, almost beyond belief. A planet the size of Earth, passing in front of a star like our own blocks, a sliver of light, so small it barely registers as a rounding error. And yet across those years of patient watching, thousands of these shadows turned up. Rocky little worlds smaller than our own planet. Gas giants dwarfing Jupiter. Planets circling so close to their star that their surfaces would glow with molten rock. Planets drifting so far out that any water on them would be frozen solid under skies that never truly brighten. When astronomers took those results and applied them across the entire stellar population of the galaxy, the conclusion was almost absurd in its generosity. On average, every single star in the Milky Way appears to host at least one planet, and a great many host several. The total number of worlds scattered through our galaxy likely runs past 1 trillion. 1 trillion planets is not a number the human mind is built to hold. So leave it as a single idea rather than a string of comparisons, and understand instead what it implies, that planet formation is not the bottleneck standing between a dead galaxy and a living one. Most of those worlds, of course, are hostile to anything resembling biology. Some orbit so close to their stars that radiation strips away their atmospheres entirely. Others sit so far out that temperatures fall to depths where any surface water would freeze into rock-hard ice. Gas giants have no solid ground at all, only atmospheres that thicken into crushing pressure the deeper you descend. But threaded between those extremes lies a narrower band, a region where a planet could plausibly hold liquid water on its surface without that water boiling away or freezing solid, a region scientists simply call the habitable zone. Liquid water is not proof of life, but it is the only known solvent in which the chemistry of every living thing we have ever studied actually works. Given a stable supply of liquid water and enough time, chemistry appears to experiment its way toward complexity with a kind of quiet persistence, and there is a great deal of time available. Even using conservative figures, something like 1 in 5 sun-like stars appears to host a rocky planet inside its habitable zone. Add in the far more numerous small red stars that make up most of the galaxy's stellar population, many of which also host rocky worlds in orbits capable of holding liquid water, and the total number of potentially habitable planets in the Milky Way climbs into the billions. Billions of worlds where water might pool into oceans, where continents might rise, where the raw chemistry of life has billions of years to run its course. Hold that number gently, because everything that follows depends on what you believe it actually means. It is worth understanding exactly how astronomers find these distant worlds in the first place, because the methods themselves reveal just how far our reach currently extends and how far it does not. The most productive technique so far has been watching for the tiny dimming of a star's light as a planet crosses directly in front of it from our point of view. A method that only works when a planetary system happens to be oriented edge-on relative to Earth, meaning it misses the vast majority of systems tilted at other angles. A second method watches for the subtle wobble a planet's gravity induces in its host star. A rhythmic back-and-forth tug that shows up as tiny shifts in the color of the star's light, stretching slightly toward red as the star pulls away and toward blue as it approaches, a pattern repeating with the planet's orbital period. This method is especially good at finding large planets orbiting close to their stars, precisely the opposite of the small, distant, rocky worlds most likely to resemble our own, which means our current catalog of planets is heavily biased toward exactly the kind of worlds least likely to host anything like the life we understand. A newer and far more difficult technique involves directly imaging a planet, blocking out the overwhelming glare of its host star well enough to capture the planet's own faint light directly. A feat accomplished so far for only a small number of especially bright, especially large, and especially well-positioned worlds. Once a promising candidate planet is found, the next and much harder question becomes whether it shows any sign of hosting life at all, and this is where the search grows genuinely difficult. Astronomers look for what they call biosignatures, chemical fingerprints in a planet's atmosphere that would be difficult to produce or sustain without ongoing biological activity. Oxygen is one of the most interesting candidates because it is a highly reactive gas that tends to disappear quickly through chemical reactions with rocks and other gases, unless something is constantly replenishing it, and on Earth, that something is photosynthetic life. Finding a planet with oxygen alongside methane in its atmosphere at the same time is considered an especially promising signal, since those two gases tend to react with and destroy each other unless something is continuously producing both. A chemical imbalance that on Earth is maintained entirely by living organisms. none of these signals are proof on their own. Some geological and atmospheric processes can mimic biological signatures without any life involved at all, which means a single detection, however exciting, requires years of follow-up observation and careful ruling out of every non-biological explanation before anyone can responsibly call it evidence of life. Even with our best current instruments, this kind of detailed atmospheric analysis is only possible for a small number of the nearest and most favorably positioned planets. And it tells us only whether simple biological activity might be present, saying nothing at all about whether a world hosts anything resembling intelligence, technology, or a mind capable of wondering about us the same way we wonder about it. The gap between finding a planet and confirming a civilization on it is enormous, and every step across that gap requires instruments more sensitive, more patient, and more precisely targeted than the ones that came before, a gap that will likely take generations of steadily improving telescopes to even begin closing. Before looking any further outward, it is worth remembering that the search for life does not only point toward distant stars. Our own solar system quietly hosts several worlds that complicate the simple picture of a habitable zone as a single band of orbits around a star. Worlds that lie far outside that comfortable band and yet may still hold liquid water and possibly life beneath their surfaces. One of Jupiter's larger moons, a small, icy world with a surface crossed by long, faint cracks, is thought to hide a deep, salty ocean of liquid water beneath a shell of ice many kilometers thick, kept liquid not by sunlight, which barely reaches that far from the sun at all, but by the constant flexing and heating caused by Jupiter's powerful gravity pulling on the moon as it orbits. A smaller moon orbiting Saturn shows even more direct evidence of this hidden ocean, actively venting plumes of water vapor and ice particles out through cracks near its southern pole. Plumes that spacecraft have flown directly through, sampling material from an interior ocean without ever needing to drill through a single kilometer of ice. Saturn's largest moon offers a different and stranger picture still. A world cold enough that water ice behaves like solid rock, yet warm enough in its own peculiar way to host lakes and rivers of liquid methane and ethane instead of water, an alien chemistry entirely its own, and one that some researchers have speculated might, in principle, support a form of biology built on entirely different molecular foundations than anything found on Earth. None of these worlds have been confirmed to host life of any kind, and each one remains extraordinarily difficult to study in detail, given how far they sit from Earth and how deeply their oceans are buried beneath thick shells of ice. But their mere existence reshapes the earlier estimate of billions of habitable worlds scattered across the galaxy, because it suggests that habitability is not limited only to planets sitting in the narrow, sunlit band, traditionally called the habitable zone. Moons warmed from within by the gravity of a large parent planet, orbiting stars of every type across every region of the galaxy, may represent an entirely separate category of potentially life-bearing world, one easily overlooked by planet-hunting surveys designed to search for Earth-sized planets crossing in front of distant stars, since a moon that small, orbiting a much larger planet, is far harder to detect at interstellar distances using our current instruments. If oceans like these turn out to be common around gas giants throughout the galaxy, and there is no obvious reason to think our own solar system is unusual in this respect, the true number of worlds capable of hosting at least simple life could run well beyond even the generous billions already estimated from habitable zone planets alone, while doing nothing at all to change the deeper problem this entire story has been building toward. Because a moon, hiding a microbial ocean beneath a shell of ice, gives you an even richer galaxy of life, without giving that life any easier way of reaching us, or us of reaching it. If life requires some fantastically rare stroke of chemical luck, then billions of habitable worlds might still produce only a small handful of living planets, each one an isolated accident in an ocean of sterile rock. But there is a clue buried in Earth's own history that argues against that idea. Our planet formed roughly 4.5 billion years ago, and for its first few hundred million years it was a battered, molten, crater-scarred place, still being pounded by leftover debris from the formation of the solar system. Yet the oldest confirmed traces of biological activity date back to roughly 3.7 billion years ago, which means life did not arrive after some long, improbable wait. It arrived almost as soon as the surface had cooled enough to allow liquid water to settle. If life truly were an astronomical fluke, you would expect it to take a very long time to stumble into existence, perhaps most of a planet's lifetime. Instead, it showed up quickly, as though the chemistry of carbon and water tends toward biology, with something close to inevitability wherever conditions allow it. That single observation has led many researchers to suspect that simple life may be common across the galaxy, arising wherever liquid water and the right raw materials persist for long enough. Intelligence is a different and much steeper question. On Earth, complex life took billions of years to arise after the first microbes appeared, and technological intelligence, the specific capacity to build tools, harness energy, and eventually transmit signals into space, emerged only once, in one branch of one species, after nearly all of that time had passed. That single data point is not much to build statistics from, but it does suggest that even if living worlds are common, worlds that produce a technological civilization may be considerably rarer. Back in 1961, an astronomer named Frank Drake proposed a simple way to organize this uncertainty: a chain of multiplied probabilities covering how many stars form, how many host planets, how many of those planets develop life, how many of those living worlds produce intelligence, how many intelligent species build detectable technology, and how long such a civilization tends to last before it falls silent. The equation does not hand you a definitive answer. Most of its terms remain genuinely unknown, and reasonable scientists plug in wildly different values depending on their assumptions. But even a deliberately cautious set of assumptions, treating intelligence and technology as rare outcomes rather than common ones, tends to produce a result somewhere in the range of a handful to a few thousand active civilizations existing in our galaxy at any given moment. Take a moderate position for the sake of argument. Suppose that out of the billions of potentially habitable worlds in the Milky Way, only about 1 in every million ever develops life at all. That alone still leaves tens of thousands of living worlds scattered through the galaxy. Suppose further that only 1 in every 1,000 of those living worlds ever produces a technological civilization. That leaves somewhere around 10 civilizations active in the galaxy right now, alongside us at this very moment. 10 sounds small next to 400 billion stars, and it is small, but 10 independently arising technological civilizations sharing a single galaxy would be one of the most significant facts in the entire history of science. It would mean intelligence is not a miracle confined to one planet. It would mean that somewhere out there, right now, another mind is looking up and asking the same question you are. And it would also mean something considerably less comforting, because 10 civilizations scattered across a galaxy this large are not neighbors. They are strangers, separated by a gulf so wide that the word neighbor barely applies. It is worth slowing down on that famous equation for a moment, because each of its individual terms hides a genuine scientific debate And understanding why those debates remain unresolved explains why estimates for the number of civilizations in our galaxy swing so wildly from one scientist to the next. The rate at which new stars form in our galaxy is the term we understand best, thanks to decades of careful survey work, and it sits at a few new stars born every year on average, a figure with relatively little uncertainty attached to it. The fraction of those stars that host planets was, until recently, the largest source of uncertainty in the entire equation, and it has effectively been resolved by the planet-hunting missions of the past 2 decades, which found that planets are not merely common but close to universal, essentially removing this term as a major source of disagreement. From here, though, the certainty collapses. The fraction of habitable planets on which life actually begins is entirely unknown, resting on a single confirmed data point, our own planet, and one data point cannot establish a rate of anything. Some researchers argue that the speed with which life appeared on early Earth suggests the process is close to automatic wherever the right chemistry and temperature persist. Others argue that Earth's early history may simply be an extraordinarily lucky exception, and that we have no way of ruling out the possibility that life is exceedingly rare, even on planets that look promising from a distance. The fraction of living worlds that go on to develop genuine intelligence is even less certain, since Earth's own history offers only a single example of a species developing complex language, abstract reasoning, and tool use to the level required for technology, out of the uncountable number of species that have existed across billions of years of evolution. Whether that outcome was a likely destination for evolution to eventually reach, or an extraordinary fluke unlikely to repeat elsewhere, remains a genuinely open question with serious scientists on both sides of the debate. The fraction of intelligent species that go on to develop detectable technology, and the average length of time such a civilization survives before falling silent, whether through self-destruction, natural catastrophe, or simply the passage of enough time that all things eventually change beyond recognition, are perhaps the most uncertain terms of all, resting entirely on assumptions about how societies behave once they gain the power to either flourish across their solar system or destroy themselves within a matter of generations. This is why the same equation, using different but equally defensible assumptions, can produce answers ranging from a single lonely civilization, meaning us, all the way up to many thousands of active civilizations scattered across the galaxy at this very moment. The uncertainty is not a flaw in the equation itself. It reflects an honest accounting of exactly how little we currently know about the rarest and most important steps along the path, from simple chemistry to a species capable of building telescopes, asking these very questions. Step back far enough, and even the Milky Way becomes a single grain of sand on a beach almost too large to comprehend. Beyond our galaxy's edge lie roughly 2 trillion other galaxies, within the portion of the universe we can currently observe, each one containing its own hundreds of billions of stars, its own trillion or so planets, its own possible collection of living and thinking worlds. The observable universe, the sphere of space from which light has had enough time to reach us since the cosmos first became transparent, spans somewhere around 93 billion light-years from one edge to the other. That number is larger than you might expect from simple multiplication of the universe's age by the speed of light, and the reason is that space itself has been stretching the entire time that ancient light has been traveling toward us, carrying its sources further away even as their light continued its long journey here. The oldest light we can detect at all, the faint afterglow left over from the universe's early hot and dense beginning, set out from matter that, at the time, sat only a few tens of millions of light-years away. That same matter, carried outward by billions of years of cosmic expansion, now sits tens of billions of light-years distant, far beyond anything we could ever hope to visit, though its ancient light still reaches us as a faint, uniform glow filling the entire sky. And this entire staggering volume, 2 trillion galaxies in all, may still represent only a small fraction of the true size of the universe. Measurements of the large-scale geometry of space suggest that the universe is flat or extremely close to it, which implies that it very likely extends far beyond the boundary of what we are able to observe, possibly by a factor of hundreds, meaning the portion of the cosmos accessible to our instruments could be a small corner of something enormously larger still. Within that observable slice alone, the numbers involved in estimating life elsewhere grow almost meaningless in their scale. If even a small handful of civilizations exist within our own galaxy at any given moment, and there are 2 trillion more galaxies, each with their own share of stars and planets, then the total number of civilizations that have ever existed across the full history of the universe could run into figures with no useful comparison left to offer. And yet, as staggering as that number might be, it changes nothing about the barriers already described. Distance within a single galaxy is difficult enough. Distance between galaxies invokes an entirely different and far harsher set of rules. Rules that do not merely make contact difficult, but in the vast majority of cases make it permanently and physically impossible, for reasons that come from the expansion of space itself. The Milky Way is not a cozy structure, edge to edge. Its disk spans somewhere around 100,000 light-years, and that disk itself is thousands of light-years thick, a flattened wheel of stars, gas, and dust rotating slowly around a central bulge. Treat that disk as a rough cylinder, and its total volume works out to something on the order of many trillions of cubic light-years, almost all of it empty space, sprinkled with stars separated from one another by gaps that dwarf the stars themselves. Scatter only 10 civilizations at random through a volume that large, and simple geometry tells you how far apart the nearest 2 are likely to be. The expected separation between the closest pair, using nothing more exotic than the statistics of random points in a given volume, comes out to somewhere in the range of 10,000 light-years. 10,000 light-years is not a distance a spacecraft crosses on a long weekend. Light itself, moving at roughly 300,000 kilometers every second, the fastest anything is permitted to travel under the laws of physics, would need 10,000 years just to make the trip one way. A radio message sent today would not arrive until 10 millennia had passed, and a reply, sent the moment it was received, would take another 10 millennia to come back. By the time an answer returned, the entire span of recorded human history would have unfolded twice over inside that single round trip. Even if the galaxy actually held far more civilizations than our cautious estimate, say 100 times as many, the nearest neighbor distance would not shrink by the same factor. Volume grows with the cube of distance, so multiplying the number of civilizations by 8 only cuts the average gap in half. Push the number all the way up to an extremely generous 1,000 civilizations, and the nearest neighbor distance still sits at roughly 2,500 light-years, a gap so large that even a signal traveling at the absolute speed limit of the universe needs 2.5 millennia just to cross it once. Picture the entire Milky Way shrunk down until it fits inside a single country, small enough to drive across in a few days. At that scale, our solar system becomes a speck too small to see, and our nearest stellar neighbor sits only a short walk away. Now scatter a handful of civilizations across that shrunken country at random. The average distance between any 2 of them works out to a long, empty walk with no roads, no landmarks, and no way of knowing which direction to even start in. Restore the galaxy to its true size. Replace that walking distance with light years, and replace the open country with hard vacuum laced with radiation. And you begin to sense the true shape of the problem. This is not a story about civilizations being rare. It is a story about a galaxy so enormous that even abundant civilizations end up profoundly alone, simply because of how much empty space surrounds each one of them. And our galaxy is only one among roughly 2 trillion others scattered across the observable universe, each separated from the next by gulfs that make even these galactic distances look almost intimate by comparison. It helps to have a clearer picture of the galaxy's actual shape before continuing, since almost every distance discussed throughout this story depends on it. The Milky Way is a flattened, spinning disk of stars, gas, and dust. Its arms curling outward from a dense central bulge in the loose spiral pattern visible in photographs of other similar galaxies seen from a distance. Our own sun sits well away from that crowded center, roughly halfway out toward the disk's outer edge, tucked inside a relatively quiet, sparsely populated spur of one of the galaxy's spiral arms, a location that, among other things, keeps us comfortably shielded from the more violent radiation and stellar crowding found much closer to the galactic core. At the very center of that bulge sits an object of enormous mass, a supermassive black hole known to astronomers as Sagittarius A. Confirmed through decades of careful observation, tracking the orbits of stars swinging around it at extraordinary speeds, definitively proving the presence of something invisible, yet powerful enough to fling entire stars into tight, rapid orbits. Reaching that galactic center from our own position takes light roughly 26,000 years, meaning any signal we send today toward the heart of our own galaxy would still be many thousands of years short of arriving, even by the time this sentence finishes. The environment near that central black hole is far more crowded and far more violent than our own quiet neighborhood. With stars packed closely enough together that gravitational interactions and intense radiation likely make conditions there considerably less favorable for the kind of slow, stable chemistry that life appears to require. This is one small reason some researchers suspect our own position within the galaxy, comfortably distant from both the chaotic center and the sparse, metal-poor outer edges, may itself be a mildly favorable location for life to arise, sitting within what some have described as a galactic habitable zone, a rough band of orbital distances around the galaxy's center, where conditions are neither too crowded and violent nor too metal, poor and raw, for rocky planets and stable biochemistry to have the best possible chance of developing over billions of years. Whether or not that idea eventually holds up to further scrutiny, it adds one more layer to the picture already built up here. A reminder that the galaxy is not a uniform field of identical stars and identical opportunities for life, but a structured, varied environment where a civilization happens to arise. Near the crowded core, out in the sparse edges, or somewhere comfortably in between, may shape its odds of ever developing at all, long before the question of ever making contact with anyone else even enters the picture. A few real examples help make all of this feel less abstract. Our nearest stellar neighbor, a small red star known as Proxima Centauri, sits a little over 4 light-years away and hosts at least one rocky planet orbiting within its habitable zone, a world close enough in principle that some of the more ambitious proposals for tiny, unmanned interstellar probes have specifically targeted it as a first real destination. Even here, at the closest possible star beyond our own, a crewed mission using anything resembling current or near-future technology would still take many thousands of years to arrive, and the planet itself, sitting close to a small, flare-prone star, may be locked with one face permanently toward its sun, raising serious doubts about whether its surface could ever support a stable, temperate environment at all. A little further out, roughly 40 light-years away, a single, small, dim star, known simply by a number and letter designation, hosts a remarkable system of 7 roughly Earth-sized rocky planets packed closely together, several of which orbit within a range where liquid water could plausibly exist. This system has become one of the most studied targets in the search for habitable worlds, precisely because it offers so many candidates in one place. Yet even this promising system suffers from the same flaring and tidal locking concerns common to small red stars. Reminders that abundance of planets does not automatically translate into genuine habitability. Slightly further away still, a planet orbiting a star, similar in size and temperature to our own Sun, was found sitting comfortably within its habitable zone, offering one of the closer analogues yet discovered to conditions on Earth. Though even confirming basic facts about its atmosphere, let alone any sign of life, remains well beyond the reach of current instruments. Every one of these systems, despite being among the closest and most promising candidates found so far, remains separated from us by distances that would take any physical mission thousands of years to cross, using propulsion methods available today or reasonably foreseeable in the near future. And these are the closest examples available, the nearest possible neighbors in the entire galaxy. The vast majority of the billions of potentially habitable worlds estimated to exist across the Milky Way sit not tens, but thousands or tens of thousands of light-years away, distances so much greater that even these already sobering travel times for our nearest neighbors would need to be multiplied many times over, stretching journeys that already exceed all of recorded civilization into spans that stretch across multiple complete rotations of our galaxy around its own center. The space between stars is not simply an absence. It is a physical environment in its own right, one with its own hazards, and it deserves to be treated as more than empty background. On average, interstellar space holds roughly 1 atom in every cubic centimeter. The air inside an ordinary room holds trillions upon trillions of molecules in that same tiny volume. So interstellar space is emptier than the finest vacuum any laboratory on Earth has ever managed to produce, thinner by a margin that is difficult to put into ordinary words. Individual atoms out there can drift for years without ever colliding with another particle. But emptiness is not the same thing as safety. High-energy particles, flung outward long ago by exploding stars and other violent events, stream through interstellar space in every direction, at every moment. On Earth, our atmosphere and our planet's magnetic field absorb the worst of this bombardment before it ever reaches the surface. A vessel out in open interstellar space has no such shield waiting for it. Scattered even more thinly are tiny grains of dust, specks of rock and carbon left over from long-dead stars, drifting at densities so low that encountering one feels like an accident. At ordinary speeds, none of this matters much. A slow-moving probe can absorb the occasional stray particle without much concern. The trouble begins the moment speed enters the picture, because at a meaningful fraction of the speed of light, even a single grain of dust carries the kinetic energy of a small explosion, and a civilization attempting real interstellar travel has to contend with that danger continuously across years or centuries of transit, not just once. And there is nothing else out there to help. No refueling stations, no rest stops, no raw materials waiting to be harvested along the way. Whatever a vessel carries when it leaves is everything it will ever have for the entire duration of the crossing. The interstellar medium does not simply separate one world from another. It actively punishes anything that tries to move through it quickly, Which brings the conversation to the next wall. One built not out of distance or hazard, but out of the very structure of space and time itself. In 1905, a young patent clerk in Switzerland published an idea that quietly closed off any easy escape from these distances. Albert Einstein was not trying to make interstellar travel harder. He was trying to understand the relationship between space, time, and light. What he found instead was that the speed of light is not just a fast measurement, it is a built-in property of space and time themselves, and nothing that carries mass can ever reach it, let alone exceed it. Light itself moves at roughly 300,000 kilometers every second, fast enough to circle the entire planet more than 7 times within a single second, fast enough that for nearly every purpose in ordinary daily life, it might as well be instantaneous. But the universe is built on a scale that exposes how finite that speed really is. Reaching even the very nearest star system takes light more than 4 years. Crossing the galaxy takes light 100,000 years. The problem is not simply that light is fast but finite. The deeper problem is what happens as any object with mass tries to approach that speed. As a spacecraft accelerates closer and closer to the speed of light, the energy required to push it even a little faster does not increase steadily. It climbs according to a curve that bends sharply upward and heads toward infinity as the ship's speed nears light speed itself. At modest fractions of light speed, this effect is a nuisance. Near the top of the scale, it becomes an absolute wall, because reaching the speed of light itself would require an infinite amount of energy for any object that has mass at all. That is not a limitation waiting on better engineering. It is closer to a law of arithmetic, as fixed as the impossibility of dividing a number by 0. Alongside this energy wall sit 2 stranger consequences of the same physics. Clocks aboard a fast-moving vessel tick more slowly relative to clocks left behind, so a crew traveling near light speed could experience a journey that feels far shorter than the years that pass for everyone they left behind. This sounds at first like a loophole, a way of cheating distance by shrinking the subjective experience of the trip, but it changes nothing about how long the outside universe has to wait. The civilization that launched the ship, and the civilization it hopes to reach, both experience the entire uncompressed duration of the journey in full, no matter how briefly it passes for the travelers themselves. Distances in the direction of travel also appear to shrink from the perspective of anyone moving fast enough, but this too is a shift in perception rather than a shortcut, because the energy required for the trip is always set by the true distance, as measured by those who stayed home, not by whatever the crew perceives from inside the ship. None of this is speculation. Particle accelerators confirm the energy curve every time they operate, pushing tiny particles to speeds within a hair's breadth of light, and finding the cost of that final sliver of speed to be almost unimaginable. Satellite clocks confirm the time distortion daily, drifting out of sync with clocks on the ground by an amount that has to be corrected for constantly, or global positioning systems would slowly fail. Special relativity is not a hypothesis awaiting revision. It is operating technology, tested to extraordinary precision, and it draws a hard line across the map of what is physically possible. Apply this to an actual voyage, and the numbers turn punishing very quickly. Take a modest interstellar vessel, something in the range of 1,000 metric tons, roughly the mass of a large naval ship, carrying a small crew, basic life support, and enough equipment to survive a long journey. Pushing that mass to just a small fraction of light speed already demands more energy than the largest weapons ever built by humanity, concentrated entirely into a single act of acceleration. Pushing it further, toward a meaningful fraction of light speed, fast enough that the trip might take centuries rather than hundreds of thousands of years, requires energy on the scale of an entire civilization's total output sustained for years at a time. Push further still, toward half the speed of light, and the energy bill climbs into a range that starts to resemble the output of a star itself, not for an instant, but sustained across the full duration of the burn. And that number only covers the payload. Any real vessel also has to carry its own fuel. And the fuel itself has mass that must also be accelerated, which means more fuel is needed to carry that fuel, and still more to carry that, in a spiral that grows worse the faster you want to go. Ordinary chemical rockets fail this test almost immediately, requiring more fuel than could ever physically fit aboard any vessel for even a modest fraction of light speed. Nuclear fusion does much better, converting a small fraction of its fuel mass directly into usable energy. And serious engineering studies from decades ago explored exactly this kind of propulsion for uncrewed probes bound for nearby stars. Even so, those studies topped out at speeds still far too slow to make a journey of thousands of light years survivable within any reasonable civilizational lifespan. Matter and its antimatter counterpart offer the most efficient fuel physics allows, converting mass entirely into energy with no waste at all. The catch is that antimatter does not exist naturally in any usable quantity anywhere we have looked, and every gram of it ever produced in a laboratory has cost vastly more energy to create than it could ever release. Other proposals try to avoid carrying fuel altogether, using powerful ground-based lasers to push a lightweight sail up to a meaningful fraction of light speed. This works beautifully for tiny, unmanned probes weighing about as much as a postage stamp. But scaling the idea up to a crewed vessel massing 1,000 tons multiplies the required laser power by a staggering, almost meaningless factor, and even then offers no way to decelerate once the destination is reached. More exotic ideas involve warping space itself rather than moving through it, an idea permitted in a narrow theoretical sense by the mathematics of general relativity, but only if a form of matter, with properties never once observed in nature, can somehow be produced in quantities rivaling the mass of an entire planet. None of these are simply engineering problems waiting for a clever solution. They are walls built directly into the physics of energy, mass, and motion, and every serious proposal for crossing interstellar distances quickly runs headlong into one of them. It helps to ground these energy figures in something a little more concrete than abstract multiples of a star's output. The largest scientific instrument ever built for studying particles, a ring-shaped accelerator buried underground in Europe, spends its entire operational life accelerating particles far, far smaller than a single grain of dust, protons so tiny that trillions of them would fit across the width of a human hair, and even then, it can only push those protons to within a hair's breadth of the speed of light, never past it, using an amount of electrical power comparable to that of a small city, concentrated entirely on particles with essentially no mass at all. Scale that same challenge up from a single subatomic particle to a vessel weighing 1,000 metric tons, roughly the mass of a large ship, and the energy requirement does not simply scale up by some modest, manageable factor. It scales up by a number so large that expressing it meaningfully requires comparing it not to a power plant, or even to every power plant on Earth combined, but to the total energy any star pours into space every single second, an amount so vast that our entire planet intercepts only a tiny, tiny fraction of it. And even that tiny fraction is enough to power every living thing on Earth, every ocean current, every storm, every gust of wind. To meaningfully approach even a modest fraction of light speed with a vessel that size requires directing an amount of energy comparable to what a star like our own sun produces over a span of years, not toward warming a planet or driving weather, but concentrated entirely into accelerating a single, modest-sized ship. This is the reason serious engineering studies of interstellar propulsion, even ones considered wildly optimistic by today's standards, tend to top out at speeds only a small fraction of light speed, because beyond that point, the energy curve does not simply get steeper, it becomes a wall that no proposed technology, however advanced, has ever offered a genuinely workable way to climb. Every additional fraction of a percent closer to the speed of light costs disproportionately more than the fraction before it, which is precisely why the handful of realistic interstellar mission concepts, seriously studied over the past several decades, have all settled for speeds that, while historic by human standards, remain far too slow to make the thousands of light years separating most civilizations survivable within any plausible lifespan. Set aside the energy problem for a moment and consider a separate question that receives far less attention: the simple matter of who, or what, actually survives a journey lasting tens of thousands of years. A crew of ordinary biological beings cannot simply endure that kind of timescale while awake, so most serious proposals for genuinely long interstellar voyages fall into one of a small number of categories, each carrying its own severe difficulties. One option is the generation ship, a vessel large enough to support an entire self-sustaining society, where the original crew's descendants, many hundreds of generations removed from the people who first launched the mission, are the ones who eventually arrive, having been born, raised, and grown old entirely within the confines of the ship. This approach solves the problem of individual lifespan, but introduces an entirely new one: the challenge of maintaining a stable, functioning society sealed inside a closed vessel for hundreds of generations without the culture drifting, fragmenting, forgetting its original purpose, or simply falling into decline the way isolated populations throughout human history so often have. By the time such a ship actually arrived, its inhabitants might have little practical understanding of the civilization that originally sent them, might not even recognize the mission's original goals as their own, and would face the destination as strangers shaped by an entirely self-contained culture rather than as representatives of whoever launched the voyage in the first place. A second option involves placing the crew into some form of long-term biological suspension, dramatically slowing their metabolism so that subjective time passes far more slowly than it does for the ship and the universe around it. No technology capable of doing this safely across tens of thousands of years currently exists, and even modest experiments with short-term suspension in other animals have revealed how difficult it is to prevent cellular damage across even a fraction of that timescale, let alone across a span longer than the entire history of human civilization. A third option abandons biological crews altogether in favor of preserving human minds in some digital or otherwise artificial form, capable of running in a dormant state for the length of the voyage and then reactivating upon arrival. This sidesteps the biological aging problem entirely, but depends on a level of technology, the ability to faithfully capture and later restore a functioning mind, that remains firmly in the realm of speculation rather than engineering, and even if achieved, still leaves unresolved the deeper question of whether whatever arrives at the destination should be considered the same traveler who set out, or something new, shaped by however many millennia its dormant state actually preserved. Every one of these approaches also has to contend with the physical demands already discussed: radiation shielding thick enough to protect fragile biological tissue or delicate electronics across millennia of exposure, mechanical systems built to function reliably far longer than any machine humanity has ever built has been asked to operate, and a closed system of food, water, and air that must sustain its passengers, whether awake, asleep, or digital, for the entire duration of a trip lasting many times longer than all of recorded history. None of this rules out the possibility of such a mission being attempted by some sufficiently advanced and sufficiently patient civilization somewhere in the galaxy. It simply adds another layer of difficulty on top of everything already discussed. One more reason why even a civilization that solves the energy problem and somehow accepts a journey lasting tens of thousands of years still has to solve an entirely separate set of problems just to ensure that anyone or anything capable of representing them actually arrives at the other end, functioning, coherent, and recognizably connected to whoever sent them. One idea that regularly comes up in discussions like this is the notion of a civilization advanced enough to capture the entire energy output of its own star, rather than the tiny fraction that happens to fall on its home planet. This concept, often described as a vast structure or swarm of collectors encircling a star to gather its light before it can escape into space, represents one of the more serious proposals for how a sufficiently advanced society might eventually gather energy on the scale required for the kind of propulsion discussed earlier in this story. Astronomers have even searched the sky for hints of such structures, looking for stars whose light appears strangely dimmed or unusually shifted toward heat in a way that ordinary natural processes struggle to explain, though every candidate found so far has eventually been traced back to a natural cause: dust, orbiting companions, or simply unusual but non-artificial stellar behavior. If a civilization did manage to build something like this, capturing the full output of a star similar to our own, it would gain access to an amount of energy so far beyond current human capability that it becomes difficult to even express meaningfully. And this is often treated as a kind of theoretical solution to the energy problem that plagues interstellar propulsion. But even this staggering level of energy control does not erase the underlying physics. A star's total output, however enormous compared to anything humanity currently commands, is still a finite number. And the earlier calculations already showed that pushing even a modest vessel to a meaningful fraction of light speed, then decelerating it again at the far end, can demand energy equivalent to years or even centuries of that star's entire output. A civilization capable of capturing an entire star's energy could, in principle, eventually afford a single such voyage, but doing so would mean redirecting the primary energy source of an entire civilization, the very thing that presumably powers its homes, its industry, and everything else it has built, toward a single one-way journey lasting tens of thousands of years, with no guarantee whatsoever that anything will be waiting at the far end. It is the difference between a wealthy nation being able to afford a single extraordinarily expensive undertaking once in a great while, and that same nation being able to casually send fleets of vessels toward every promising signal detected across the sky. Harnessing an entire star does not turn interstellar travel into something routine. It turns it into something occasionally, barely possible, for a narrow set of destinations, chosen with extraordinary care, undertaken perhaps once or twice across the entire lifespan of a civilization, rather than as an ordinary part of its daily existence. This distinction matters enormously, because contact between civilizations is not a single event. It requires many opportunities, many attempts, many independent efforts, succeeding across a long span of time to produce even one confirmed meeting, and a technology that allows for only one or two attempts across an entire civilization's existence, however advanced. still leaves the overall probability of any particular pair of civilizations actually meeting extraordinarily low. There is an additional wrinkle in the radiation problem that deserves its own attention, because the obvious solution, simply adding more shielding around a vessel, runs directly into the same energy trap already described. Shielding a crew or sensitive equipment against the intense radiation encountered at a meaningful fraction of light speed requires thick layers of dense material positioned between the hazard, whatever needs protecting. And thickness in this context means mass, often a great deal of it. But every additional unit of mass added to a vessel has to be accelerated right alongside the crew and cargo, which means more shielding directly increases the total energy required for the journey, which, in turn, through the same compounding fuel problem already discussed, demands even more fuel to carry that additional mass, which itself needs to be shielded and accelerated in turn. Engineers working through early theoretical designs for fast interstellar probes have consistently run into this same tension, finding that the shielding required to make a multi-decade journey survivable for a human crew adds so much mass that it can easily double or triple the total energy budget already calculated. Bare vessel alone, on top of every other requirement already stacked into that budget. One proposed workaround involves using the ship's own fuel supply as a form of shielding, positioning tanks of water or fuel between the crew and the direction of travel. Since these materials happen to be reasonably effective at absorbing high-energy particles, this helps somewhat, but does not eliminate the underlying tension, since large fuel supplies are already required for propulsion in the first place, and any additional fuel carried purely for its shielding properties still adds mass that must be accelerated across the same punishing energy curve. The uncomfortable truth is that there is no way to simply engineer around this problem by adding a clever new material or a smarter design. Every gram of protection costs energy to carry, and every gram of energy required to carry it comes from the same limited well, already strained by the propulsion requirements alone, which is one more reason serious proposals for genuinely fast interstellar travel tend to favor small, unmanned probes over large, crewed vessels. Since a probe carrying instruments, rather than a fragile human crew, can tolerate far higher radiation doses without needing anywhere near the same mass of shielding. Sidestepping this particular trap even while remaining unable to solve the deeper problem of ever bringing two civilizations into actual physical contact with one another. Even setting distance and energy aside for a moment, there is a third barrier waiting, and it may be the cruelest of the three, because it operates in time rather than space. Picture an enormous apartment building with thousands of units, and imagine that every tenant is only ever home for a few scattered minutes out of an entire year, arriving and leaving at completely random moments with no shared schedule of any kind. The building is full. You can sometimes hear faint signs of activity through the walls, but you could live there for decades and never once be home at the same moment as another tenant, not because the building is empty, but because each window of presence is so brief and so randomly placed that overlap becomes an extraordinary rarity. This is close to the situation facing civilizations scattered across a galaxy that is roughly 13 billion years old. Our galaxy began assembling itself within the first billion years after the universe existed at all, and the heavier elements needed for rocky planets and organic chemistry, elements like carbon, oxygen, and iron, were only cooked up gradually inside generations of stars that lived and exploded long before our own sun ever formed. Earth itself is about 4.5 billion years old. Life appeared within the planet's first billion years, and creatures capable of building tools and sending signals into space have existed for only the tiniest closing sliver of that entire timeline. A span so short that if the galaxy's full history were compressed into a single calendar year, human technological civilization would occupy only the last fraction of a second before midnight on the final day. There is no strong reason to assume our own case is unusual. Natural disasters capable of resetting a planet's biological progress, a large asteroid strike, a nearby stellar explosion, occur on timescales of many millions of years, often enough that any civilization enduring for a very long stretch will eventually face one. Civilizations may also face risks of their own making, environmental strain, conflict, or the unpredictable consequences of their own advancing technology, all of which tend to play out across centuries rather than across the deep stretches of geological time. Even granting a wildly generous assumption that the average technological civilization somehow persists for a full million years, far longer than humanity has existed in any recognizable form, the mathematics of overlap remain harsh. A million years is a vanishingly small sliver of a 13-billion-year-old galaxy, and two civilizations arising at random points across that vast span have only a slim chance of their windows of existence overlapping at all. Even when their existence does overlap, the journey between them, tens of thousands of years at minimum given everything already discussed about distance and energy, may easily outlast the remaining span of either civilization's overlap window. A signal detected from far away tells you only what conditions looked like when that light left its source, long before it ever reached your telescope. And by the time any vessel could cross that gap in response, the world it was aiming for might have fallen silent long ago, its atmosphere quietly settling back into a lifeless chemical balance, its cities, if it ever built any, long since gone. Or the destination might simply not be ready yet, its own civilization still tens of thousands or millions of years from ever existing at all. The window that allows two civilizations to actually meet is not set by distance alone, nor by energy alone, but by the narrow intersection of both civilizations existing at the same cosmic moment, close enough for the journey between them to fit inside whatever time remains before one of them falls silent. There is one more clock running quietly beneath everything discussed so far, a clock that governs not any single civilization or any single star, but the entire era of the universe during which stars, planets, and life of any kind are even possible in the first place. The universe is currently around 13.8 billion years old, and by cosmological standards it is still remarkably young, sitting near the beginning of what astronomers sometimes call the stelliferous era, the long stretch of cosmic history during which stars are actively forming, burning, and providing the light and warmth that any form of life depends on. This era is expected to continue for an almost unimaginable span of time, with new stars still forming from the galaxy's remaining reserves of gas for perhaps another trillion years or more, though the rate of that formation is already slowing as the raw material for new stars is gradually consumed and dispersed. Small, frugal stars, the dim red ones that make up the majority of the galaxy's stellar population, will continue burning far longer than any current estimate of a civilization's lifespan could meaningfully account for, some of them persisting for trillions of years, offering in principle an extraordinarily long window during which new civilizations could still arise around them long after stars like our own sun have gone quiet. Eventually, over spans of time that dwarf even the current age of the universe many times over, star formation will slow to a trickle and then stop almost entirely as the available gas is used up, and the galaxies of the universe will contain only the dimmest, longest-lived stars, slowly fading toward exhaustion over trillions of additional years. This matters for the story of contact between civilizations because it means the window for life and intelligence to arise at all, though it may feel to us like it has already stretched across an almost incomprehensible span of galactic history, is itself only a portion of a far longer era still to come. Civilizations arising early in this era, as we appear to be doing now, share the universe with countless other stars still in their infancy, waiting billions of years for their own planets to cool, their own oceans to form, and their own chemistry to begin experimenting toward life. Civilizations that might arise deep into that far future, orbiting stars that have not even finished forming yet at the moment you are hearing this, would exist so far removed from us in cosmic time that no signal, no vessel, and no form of contact of any kind could ever hope to bridge that gap, not because of distance or energy, but simply because we would already be long gone by the time they existed at all. Time, in other words, is not simply a barrier measured in the tens of thousands of years it takes to cross a gap between neighboring stars. It is a barrier woven into the entire lifespan of the universe itself, ensuring that even within a single galaxy, civilizations are scattered not only across an enormous volume of space, but across a truly vast depth of cosmic time, most of which has not even happened yet. Stars themselves add another layer to this problem, because they are not permanent fixtures either. A star's mass determines how long it burns, and the relationship is steep rather than gentle. A star, noticeably heavier than our own sun, burns through its fuel far faster, sometimes finishing its entire hydrogen-burning life in a couple of billion years or less, which may simply not leave enough time for complex life to evolve before conditions around it change beyond recognition. Our own sun, a fairly ordinary star, has a total main sequence lifespan of roughly 10 billion years, and it is already about halfway through that budget. Long before it actually runs out of fuel, its slowly rising output will make its inner planets uninhabitable, which means the true habitable window for a world like ours is measured in a bit over 1 billion years, not the full 10. Smaller, dimmer stars burn far more slowly, some of them capable of shining steadily for over 1 trillion years, offering in principle an enormous window for life to develop. But these small stars bring their own complications, tending to sit close enough to their planets that those worlds may become locked with one face permanently toward their star and one face in permanent darkness, and tending to erupt in violent flares far more often than calmer stars like our own. Flares capable of stripping away a planet's atmosphere over time. The upshot is that habitable windows are scattered unevenly across both space and time, opening around some stars billions of years ago and closing long before our own sun even existed, opening around other stars only recently, and not yet opening at all around stars, still too young for their systems to have settled into anything resembling stability. Two civilizations must not only exist at the same cosmic moment, they must also have arisen around stars whose habitable windows actually overlap, which rules out an enormous number of otherwise promising pairings before the conversation about distance or speed even begins. Stars also do not sit still. Our own sun orbits the center of the galaxy at more than 200 kilometers every second, completing one full circuit only after hundreds of millions of years, drifting up and down through the galactic disk along the way, and occasionally being nudged off course by the gravity of passing clouds of gas or the slow churn of the galaxy's spiral arms. Over a journey lasting tens of thousands of years, a destination star can drift many light-years from wherever it appeared to be when the voyage began, which means any vessel attempting a truly long crossing is not aiming at a fixed point at all, but at a moving target whose future position becomes harder to predict the further into the future you try to look. There is a famous story from the middle of the last century that captures this puzzle better than any equation. A group of physicists were having lunch together, casually discussing the possibility of faster-than-light travel and the likelihood of other civilizations, when one of them, the Italian physicist Enrico Fermi, apparently paused and asked a simple question. If the galaxy is old enough and large enough for advanced civilizations to have arisen many times over, where is everybody? The question sounds almost naive at first, but it points directly at a genuine tension. Even a civilization expanding slowly, using nothing more exotic than slow, sublight probes that build copies of themselves at each new star system they reach, could, in principle, spread across the entire galaxy in only a few tens of millions of years, a modest span compared to the galaxy's full 13-billion-year history. If even one civilization anywhere in the galaxy's long past had done this, the argument goes, evidence of its presence should be everywhere. Yet the sky, at least so far, appears silent. Scientists have proposed a wide range of explanations for that silence over the decades since, and it is worth walking through a few of them because each one quietly supports a different piece of the picture already built up here. One explanation, sometimes called the Great Filter, suggests that some step along the road from simple chemistry to a galaxy-spanning civilization is extraordinarily difficult to pass. So difficult that almost nothing manages to get through it. That filter might already be behind us, meaning the origin of life itself, or the jump from simple to complex cells, is the rare and difficult step. And once a planet clears it, intelligence and technology tend to follow relatively easily. Or the filter might still be ahead of us, meaning many worlds reach something like our own level of technological development, only for nearly all of them to destroy themselves shortly afterward through war, environmental collapse, or some other self-inflicted catastrophe before they ever manage to expand beyond their home star. Another explanation, sometimes called the rare Earth hypothesis, argues that while simple life may be common, the specific combination of conditions required for complex, intelligent life is so demanding: a stable orbit, a large moon to steady a planet's tilt, plate tectonics to recycle carbon, a well-timed sequence of evolutionary accidents, that intelligent life of any kind is far rarer than the raw numbers of habitable worlds would suggest. A third explanation simply accepts that civilizations are common, but argues, using exactly the physics already laid out here, that the combination of distance, energy, and time makes contact between any two of them extraordinarily unlikely, even when both exist. Under this view, the silence is not a mystery at all. It is precisely what you would expect from a universe filled with life that is nonetheless structured to keep almost all of that life apart. None of these explanations require abandoning the idea that the galaxy holds other minds. They simply require accepting that abundance and accessibility are two entirely separate questions, and that the second one is governed by physics far less forgiving than the first. Search efforts on Earth have spent decades scanning the sky for radio signals or laser pulses that might indicate an artificial source, listening across enormous stretches of the radio spectrum and monitoring millions of star systems in the hope of catching a single, deliberate transmission. So far, nothing conclusive has turned up, and given everything already discussed about distance, timing, and the narrow windows during which any two civilizations might both be broadcasting and listening at once, that absence of a detected signal is exactly what the mathematics would predict, whether the galaxy is nearly empty or quietly full. There is one more explanation for cosmic silence worth setting alongside the physical barriers already described, if only because it takes such a different view of why contact might never happen. Some thinkers have proposed that the universe's silence is not an accident of distance or physics at all, but a deliberate strategy. The idea that any sufficiently advanced civilization would recognize contact with an unknown neighbor as a potential threat rather than an opportunity, and would therefore choose to stay quiet, hidden, and unresponsive rather than risk revealing its location to something that might prove hostile. Under this view, sometimes called the dark forest idea, the galaxy is imagined as a dark wilderness full of quiet hunters, each one aware that announcing its presence could invite a danger it has no way of enticing or defending against. And so every civilization chooses silence as the only rational strategy for survival. It is a genuinely unsettling idea, and it has captured a great deal of popular imagination, but it sits somewhat uneasily alongside the physics already laid out across this entire story. If two civilizations are separated by thousands of light years, are unlikely to even exist during overlapping windows of time, and would each need energy on the scale of a star's total output just to send a slow-moving vessel one way, the practical danger posed by any one civilization to another shrinks dramatically compared to the danger implied by deliberate, coordinated hiding. A threat that takes tens of thousands of years to arrive, assuming it could be organized and afforded at all, is not the same kind of threat that would justify a species abandoning all outward communication out of pure survival instinct. The barriers already discussed here, the sheer size of the galaxy, the speed of light, the exponential cost of approaching it, the brief and poorly overlapping windows of civilizational existence, and the expanding gulf between galaxies, are sufficient on their own to explain a silent sky, without requiring any civilization to be actively and successfully hiding at all. This does not mean caution or restraint plays no role whatsoever in how a civilization might choose to broadcast its presence. It simply means that the silence observed so far does not require a galaxy full of frightened, hidden hunters to explain it. A galaxy that is simply very large, very old, and governed by physics that makes contact difficult, produces exactly the same observed silence as a galaxy full of civilizations, deliberately choosing not to speak. And distinguishing between those two explanations from where we currently sit is, for now, essentially impossible. What can be said with more confidence is that the structural explanation, distance, physics, and time, working together rather than any deliberate concealment, requires no assumption about the psychology or intentions of civilizations we have never observed and know nothing about. It rests entirely on laws of physics we have already tested and confirmed here at home, which makes it, at the very least, the explanation that asks us to accept the fewest unproven assumptions in order to make sense of a quiet and largely uneventful sky. There is one more subtle problem hiding inside the search for a detectable signal, separate from distance and timing, and it concerns the kind of technology any two civilizations happen to be using at the exact moment their windows of existence overlap. Humanity has only been capable of sending or receiving radio signals for a little over a century, and there is no strong reason to expect that radio will remain our primary method of communication indefinitely. Within our own short history, we have already moved from simple radio broadcasts toward more efficient, tightly focused methods of transmitting information, methods that leak far less, signal out into space accidentally, precisely because they are more efficient at delivering information only to an intended receiver rather than scattering it wastefully in every direction. If this trend continues, it raises an uncomfortable possibility that the era during which any civilization broadcasts loudly and accidentally enough to be detected by someone else entirely by chance might be quite brief, a narrow technological phase that a civilization quickly moves through and then leaves behind in favor of quieter, more efficient methods once it matures. A civilization only a few centuries ahead of us in its own development might already have abandoned the kind of broadcast radio signals we are currently capable of detecting, having shifted toward communication methods so efficient, so tightly focused, or so unfamiliar in their underlying physics that our current instruments would not even recognize them as artificial at all, let alone decode any information from them. Conversely, a civilization only a few centuries behind us might not yet have developed radio technology at all, meaning it could be thriving, complex, and biologically rich, yet completely silent and undetectable by any method currently available to us, not because it is hiding and not because it does not exist, but simply because it has not yet reached the particular narrow technological stage that happens to produce the kind of signal we know how to look for. This means the already narrow window during which two civilizations must both exist and be located within survivable distance of each other is narrowed further still by the requirement that both happen. To be using compatible, mutually detectable technology at the exact same moment, a condition with no guarantee of holding even when every other condition has somehow already been met. It is entirely possible that the galaxy has, across its long history, contained many civilizations that briefly passed through a radio-bright phase similar to our own, each one leaking signals into space for a century or two before advancing beyond it, meaning their signals swept past Earth long before humanity ever built an instrument capable of detecting them, or will sweep past at some point in the distant future, long after any instrument we currently operate has been replaced by something else entirely. Detecting another civilization, in other words, does not simply require that civilization to exist and be close enough to reach. It requires a genuinely narrow coincidence of technological timing, layered directly on top of every other coincidence already required, one more dial that must land on the correct number at the exact same moment as all the others, in a search where almost every condition involved seems to conspire towards silence rather than contact. None of this means every form of contact is equally impossible, and it is worth drawing a clear line between the two very different kinds of reaching out discussed throughout this story. Physical travel, an actual crewed vessel departing one star system and arriving at another, carries every burden already described. The energy cost of approaching light speed, the radiation and dust hazards of the journey itself, the challenge of keeping any crew or mind functional across tens of thousands of years, and the risk that whoever sent the vessel, or whoever it was sent to find, no longer exists by the time it arrives. A simple radio or laser signal carries almost none of that burden. It requires no fuel beyond what it takes to transmit, no life support, no shielding against decades of cosmic ray bombardment, and it already moves at the one speed nothing can exceed, the speed of light itself. For civilizations separated by a few dozen or even a few hundred light years, rather than the thousands separating the average pair of civilizations across the whole galaxy, an exchange of signals becomes a meaningfully different proposition than an exchange of ships. A message sent today to a star, 100 light-years away, arrives in 100 years, and a reply could be back within 2 centuries, a long wait by any human standard, but a wait that fits, at least in principle, within the kind of civilizational lifespan that appears plausible rather than requiring the tens of thousands of years demanded by physical travel across the galaxy's true average separation. This is precisely why the search for radio or laser signals, rather than the search for physical spacecraft, has occupied most of humanity's actual effort in this area so far. It is the one avenue where the timescales involved, while still long by any single human lifetime, Do not immediately collide with the harshest of the barriers already discussed. Even here, though, the same fundamental problem of overlapping windows applies. Both civilizations still need to exist, be listening, and be transmitting during a shared window of time narrow enough to fit within the light travel times separating them, and the vast majority of possible pairings across the galaxy remain separated by distances measured in thousands of light years rather than the mere hundreds that make an exchange of information at all practical within any reasonably imaginable civilizational lifespan. So the honest picture that emerges from all of this is not one of complete and total impossibility in every direction. It is a picture in which physical meetings between two independently arisen civilizations are, for all practical purposes, ruled out by the combined weight of distance, energy, and time, while a narrow, difficult, but not entirely closed door remains open for the exchange of information alone, and only for those rare pairings of civilizations who happen to sit close enough and exist at close enough moments in cosmic history for even light itself to make the round trip worthwhile. Given everything already laid out, an interesting and genuinely unresolved debate has grown up among scientists over whether humanity should even be actively broadcasting messages outward at all, rather than simply listening. Passive listening carries essentially no risk, since it involves nothing more than pointing sensitive instruments at the sky and analyzing whatever arrives naturally, without ever revealing our own location or capabilities to anyone. Deliberately transmitting a message outward, sometimes described as active searching rather than passive listening, involves a different calculation entirely, since it means intentionally announcing our presence, our location, and something about our own level of technological development to whoever might eventually receive it. Some researchers argue this carries little practical risk, precisely because of everything already discussed in this story, given that any civilization capable of receiving such a message and doing anything about it would likely be separated from us by thousands of light years, meaning any response, friendly or otherwise, would take so long to arrive that it poses no meaningful danger to anyone currently alive or likely to be alive when it does. Others argue for caution, regardless, reasoning that we cannot know in advance what kind of civilization might eventually receive such a signal, nor what its intentions or capabilities might be, and that the enormous time delays involved cut both ways, meaning any mistake made today could not be corrected or withdrawn for tens of thousands of years, long after the people who made the original decision are gone. This disagreement has occasionally spilled out of academic circles and into public debate, with some serious voices in astronomy openly disagreeing on whether an occasional handful of deliberate, targeted transmissions sent by human scientists over past decades were wise decisions or unnecessary risks. The debate itself is a useful reminder that even setting aside the physical barriers explored throughout this entire story, the question of contact carries genuine ethical weight, not because contact is likely to happen anytime soon, but because the decisions being made today about what to send, how loudly to send it, and in which direction, are decisions whose consequences, if they ever arrive at all, will not be felt for longer than the entire span of recorded human history so far, inherited by descendants who had no say in the choice at all. It is one more way in which the sheer scale of these distances reshapes an otherwise ordinary scientific question into something closer to a responsibility passed down across an almost unimaginable stretch of future generations. Humanity has already made a handful of small, almost symbolic attempts to reach across this gap, and looking at them honestly says as much about the scale of the problem as any equation does. In the 1970s, 2 robotic probes left our solar system carrying golden phonograph records, each engraved with sounds and images meant to represent life on Earth, greetings recorded in dozens of languages, music ranging from classical compositions to folk songs, photographs of forests, cities, and human faces. All sealed inside a metal case designed to survive the vacuum of space for an extraordinarily long time. Those two probes are still traveling outward today, decades later, and yet in the entire span of their journey so far, they have covered only the tiniest fraction of the distance to even the nearest other star system. A reminder of just how slow ordinary spacecraft actually are once you compare their speed to the true scale of interstellar distance. At their current pace, it would take those probes tens of thousands of years just to pass anywhere near another star, and by the time they arrived in that star's general vicinity, there would be no way of steering them toward any specific planet at all, since they carry no fuel for course correction across a journey that long. Around the same era, scientists at a large radio observatory transmitted a single, carefully constructed message toward a distant cluster of stars, encoding basic facts about human biology, our solar system, and our own chemistry into a pattern of radio pulses aimed outward into the sky. That message is still traveling, and given the distance to its target, it will not arrive for tens of thousands of years, and any reply, sent the moment it was received, would not reach us for tens of thousands of years after that, meaning nobody who sent that message, nor anyone who will ever be born on this planet in any foreseeable future, will ever know whether it was received at all. More recently, dedicated listening programs have used powerful radio telescopes to scan enormous stretches of the sky, searching for any signal that might indicate an artificial, intelligent source somewhere among the stars, quietly sifting through the natural noise of the universe in the hope of finding a single deliberate pattern. These efforts represent humanity's most serious attempts so far to bridge the gap discussed throughout this entire story, and every one of them runs directly into the same walls. The distances are too vast for anything but a message to have any hope of crossing them in a survivable amount of time. Even a message takes so long that neither the senders nor their descendants, for many thousands of generations, will ever learn whether it was received, and the fraction of the sky and the fraction of possible frequencies that any listening program can actually search, even using the most advanced instruments on Earth, remains a vanishingly small slice of everything that could theoretically be out there. None of this makes the effort meaningless. It simply places these attempts in their proper context, not as first contact waiting to happen within a human lifetime, but as messages in bottles thrown into an ocean so large that whether they are ever found may not be answered for longer than civilization itself has yet existed. Given everything laid out so far, it is worth asking a more practical question than whether we will ever meet another civilization, and that is what a realistic search for life should actually be aiming for in the near term. The honest answer looks very different depending on whether the target is simple life or intelligent life, and the difference in difficulty between the two is not a matter of degree, it is a difference in kind. Detecting simple, microbial life within our own solar system requires physically reaching a handful of specific worlds, drilling or sampling material from beneath an ice shell or within a plume of vapor, and running direct chemical tests on the material collected. A genuinely difficult engineering challenge, but one that falls well within the reach of missions already being planned or actively developed using current or near-future technology. Detecting simple life on a planet orbiting another star is harder, relying entirely on remote analysis of that planet's atmosphere from many light-years away, watching for the kind of chemical imbalances discussed earlier that suggest ongoing biological activity, a task that will likely occupy the next generation of space telescopes for decades to come. slowly building a catalog of candidate worlds and painstakingly ruling out non-biological explanations for each interesting signal found. Detecting intelligence is an entirely different undertaking again, requiring either a deliberate signal sent by that intelligence and captured during the narrow window in which both sender and receiver happen to be listening, or physical evidence of large-scale engineering visible from an enormous distance, something like an unusually dimmed star or an unusual pattern of infrared light, suggesting a structure built to capture stellar energy. Evidence that, as already discussed, has never yet turned up despite decades of searching. Given the layered barriers explored throughout this entire story, distance, energy, mismatched cosmic timing, and the ever-widening gulf created by the expansion of the universe itself, it becomes clear that finding simple life, whether within our own solar system or on a planet orbiting a distant star, is by far the more achievable goal likely to be reached, if it happens at all, well within the coming decades. Finding evidence of another intelligent civilization, let alone ever physically meeting one, may remain out of reach, not for decades, but for the entire remaining span of human civilization, regardless of how advanced our instruments eventually become, simply because the barriers involved are not questions of instrument sensitivity at all, but questions of fundamental physics that no amount of clever engineering can circumvent. None of this makes the search worthless. Every answer, even a repeated absence of any signal, narrows the range of honest possibilities and sharpens the picture of exactly how rare, or how common, life and intelligence actually are across the galaxy, and even confirming a single instance of simple microbial life on another world entirely separate from our own would settle, once and for all, the question of whether life is a common outcome of ordinary chemistry or a genuine rarity confined to a single lucky planet. That alone would be one of the most significant discoveries in the entire history of science. Even without a single conversation, a single handshake, or a single physical meeting ever taking place. To feel the weight of these numbers rather than simply hear them, imagine one specific attempt at contact played out from beginning to end. A civilization somewhere in the galaxy, perhaps not so different from our own in its ambitions, detects an unusual signal from a star system a few thousand light-years away. A pattern too regular to be natural, a faint suggestion that something intelligent once produced it. Excited by the discovery, this civilization spends centuries developing propulsion technology capable of reaching a meaningful fraction of light speed, pouring the equivalent of years of its entire planetary energy output into a single vessel, and finally launches a crewed mission toward the source of the signal. The journey, even at a hard-won 10% of light speed, takes tens of thousands of years. The crew, whether kept in some form of long-term suspension or replaced across many generations born and raised aboard the ship, endures a voyage longer than the entire span of human civilization to date, threading through radiation and dust for the whole of that time, trusting that whatever they detected all those centuries ago will still be waiting when they arrive. Eventually, after tens of thousands of years, the ship reaches its destination. It settles into orbit around the planet that once produced that curious signal, and its instruments begin to scan the surface. What they find is silence. The atmosphere shows no trace of the artificial gases that first caught their ancestors' attention. There are no lights visible on the planet's night side, no structures, no further transmissions of any kind. Whatever built that signal is gone, whether through some natural catastrophe, some slow ecological collapse, or its own internal history playing out to its end, long before this ship ever left home. The travelers have crossed tens of thousands of years of empty space to arrive at a grave, one so old that even the memory of what happened has faded from the world itself. leaving only a planet slowly settling back into a lifeless chemical balance. Or picture a gentler variation of the same story. The ship arrives to find a planet full of life, oceans, forests, complex ecosystems thriving under an unfamiliar sky, but no sign of the civilization it set out to find. Perhaps that civilization existed exactly where the signal suggested, flourished for a while, and quietly came to its own end long before the ship arrived. Its former home world simply continuing on without it, filling the gap it left behind with new, uncomprehending forms of life. Neither outcome requires any villain, any catastrophe of malicious intent, any grand galactic conflict. Both are simply the ordinary consequence of sending a message and a mission across a gap so wide that by the time either one arrives, the other side of the conversation has already moved on, one way or another, into whatever comes next. This is the shape of contact across galactic distances, not a meeting, but an echo arriving long after the voice that made it has already fallen silent, and there is no way to know in advance, from here, whether that silence will be waiting when the journey finally ends. There is one final barrier, and it does not belong to distance, energy, or time in the ordinary sense. It belongs to the geometry of the universe itself. Back in the late 1920s, observations confirmed that distant galaxies are all moving away from us, and that the farther away a galaxy sits, the faster it appears to retreat. This was not galaxies flying apart through a fixed and unchanging space. It was the space between them stretching, carrying galaxies apart, the way dots drawn on the surface of a balloon spread further apart as the balloon itself is inflated. Close to home, this effect is negligible. Our nearest large neighboring galaxy is actually falling toward us under gravity rather than drifting away. But at distances of hundreds of millions of light-years and beyond, the stretching of space begins to dominate, and galaxies out there recede at thousands of kilometers every second, with the very furthest visible galaxies retreating at speeds approaching, and in many cases exceeding, the speed of light itself. This does not break the cosmic speed limit, because nothing is actually moving through space faster than light. Those distant galaxies sit still relative to their own surroundings. It is the space between them and us that is expanding so quickly that the total gap grows faster than light could ever cross it. Beyond a certain distance, a beam of light aimed directly at us will simply never arrive, not because it slows down or fades away, but because the space it must cross keeps growing faster than the beam can cover it. There is no clever trick, no relay, no future technology that gets around this. It is a geometric fact about an expanding universe, and it means that a huge share of the galaxies we can currently observe are already retreating faster than light, visible to us only because their light set out long ago, before the gap had grown so wide. Their present moment is already forever out of reach. Making this worse, the expansion of the universe is not slowing down the way gravity alone would suggest it should. Since the late 1990s, careful observations of distant exploding stars have shown that the expansion is actually speeding up, driven by a mysterious, pervasive component of the cosmos that makes up most of the universe's total energy content and does not thin out as space grows, meaning the more space that exists, the stronger its outward push becomes. One direct consequence of this accelerating expansion is that a boundary called the cosmic event horizon is slowly closing in. Galaxies currently within our reach are being carried across that boundary at an increasing rate, and once a galaxy crosses it, no signal it ever sends, no light it ever produces, will ever reach us again. It does not vanish in a flash. Its light simply stretches and dims into invisibility over time, but the outcome is the same: a permanent and irreversible end to any possible connection. Within our own small local cluster of galaxies, gravity still holds everything together tightly enough to resist this stretching, which is the only reason distances within our own galaxy remain governed by the earlier barriers of speed, energy, and time, rather than by this one. But for the overwhelming majority of galaxies in the wider universe, contact of any kind, physical or otherwise, is not merely difficult. It is, and will remain, flatly impossible. Our own galaxy is not entirely alone, even in this picture of accelerating separation, because it belongs to a small cluster of several dozen galaxies, bound together tightly enough by their mutual gravity that the stretching of space between them has essentially no effect at all. Chief among our companions is the large spiral galaxy Andromeda, sitting a little over 2 million light-years away and, unlike almost everything else in the wider universe, actually moving toward us rather than away, pulled inward by the combined gravity of both galaxies. In roughly 4 to 5 billion years, our two galaxies will begin to merge, their stars sliding past one another in a slow gravitational dance that will eventually reshape both into a single larger galaxy. An event violent in cosmic terms but almost entirely uneventful for any individual star system caught up in it, since the distances between stars remain so vast that direct collisions between them are exceedingly rare, even during a full galactic merger. Any civilization living through that merger, whether descended from our own or from something that arose independently around Andromeda, would witness a genuinely spectacular transformation of the night sky, unfolding gradually over hundreds of millions of years rather than as any sudden event, as two great spiral structures gradually became one. Beyond that merged galaxy, however, the future grows steadily emptier. As the accelerating expansion of the universe continues, every other galaxy currently visible from Earth will slowly cross beyond the cosmic horizon already discussed, redshifting into invisibility one by one across time, spans measured in tens and eventually hundreds of billions of years. The nearest large cluster of galaxies beyond our own group, a rich collection sitting roughly 50 million light-years away, will likely cross that horizon within about 100 billion years from now, its many thousands of stars and any civilizations they might harbor, slipping permanently beyond any possible future contact. A more distant and even larger cluster, several 100 million light-years away, will cross even sooner. Its greater distance meaning it is already receding from us that much faster. Long before either of those crossings occurs, any observers living in our merged future galaxy will find the sky growing quieter and darker by degrees. Not through any single dramatic event, but through the slow, steady erasure of ever more distant lights as the universe methodically seals off one section of itself after another. Eventually, over a span of time almost too long to meaningfully compare to anything, observers in that far future galaxy would see nothing at all beyond their own stars. No other galaxies, no trace that the universe was ever anything other than a single, lonely island of light floating in an otherwise empty and static-seeming void, with no observational evidence remaining that the wider cosmos, the 2 trillion other galaxies, the ancient afterglow of the universe's early history, or any of it had ever existed at all. This distant future carries a strange kind of symmetry with the question at the heart of this entire story. In this present era of cosmic history, the universe still allows us a genuine view of an enormous and richly populated cosmos, 2 trillion galaxies worth of raw material for life and possibly civilization. That view itself is temporary, a fleeting privilege belonging to observers who happen to exist during the relatively narrow window before expansion quietly closes the curtain on all of it. Put the whole picture together and something becomes clear. This is not one obstacle. It is several, stacked on top of each other, each one arising from a completely different area of physics, each one capable on its own of preventing contact, and together forming a barrier far stronger than the sum of its parts. The sheer size of the galaxy scatters even a healthy population of civilizations across distances of thousands of light years, simply because of how much empty volume surrounds every single star. The speed of light sets an absolute ceiling on how fast anything with mass can ever travel, a ceiling confirmed by more than a century of experiments and never once bent. The energy required to approach that ceiling rises so steeply that even a modest vessel demands resources on the scale of an entire star's output, a bill that grows worse the moment you also account for the fuel needed to carry more fuel. Civilizations themselves appear to exist for only the briefest sliver of galactic time, meaning that even two worlds separated by a survivable distance may simply miss each other by tens of thousands or millions of years. Stars carry their own expiration dates, opening and closing habitable windows unevenly across billions of years of galactic history, so that even nearby worlds may belong to entirely different eras. And beyond the edge of our own small, gravitationally bound neighborhood, the expansion of the universe itself severs any possible connection permanently, growing the gap between galaxies faster than anything could ever cross it. A civilization that somehow solves the energy problem still runs into the speed limit. One that somehow reaches a meaningful fraction of light speed still runs into the mismatch of timing. One that happens to share a moment in time with a neighbor still has to physically survive the crossing. And one that exists in another galaxy entirely runs straight into a wall that no future technology, however advanced, will ever be permitted to breach. None of these barriers competes with the others for the title of biggest obstacle. They cooperate, each one closing off whatever narrow path might have slipped past the barrier before it, until the combined probability of two independently arising civilizations ever actually meeting becomes so small that across the entire history of a galaxy this size, it may simply never happen, not even once. It helps to understand exactly why stacking several difficult conditions together produces an outcome so much rarer than any single condition on its own. Imagine a lock that only opens if 6 separate dials, each one spun independently, all happen to land on the correct number at the exact same moment. Getting any single dial to land correctly might not be so unlikely on its own, but requiring all 6 to align at once multiplies those individual odds together, and even 6 conditions that each have a reasonably good chance of succeeding on their own can combine into an overall probability so small that the lock might realistically never open at all, across entire lifetime of whoever is trying. That is essentially the situation facing any two civilizations hoping to physically meet. They must happen to arise close enough together in space that the resulting distance is survivable at all. They must happen to exist during even a partially overlapping stretch of cosmic time. They must both arise around stars whose habitable windows overlap with each other. Whichever one attempts the journey must command energy resources on a scale that, as already discussed, may require harnessing the output of an entire star. Whatever vessel or signal they send must survive the actual crossing, whether that means enduring decades of radiation and dust impacts or simply not being lost to some failure across tens of thousands of years of unattended operation. And the destination civilization must still exist, recognizably itself, and still listening or watching, at the exact moment any signal or vessel finally arrives. Each of these conditions on its own might not sound impossibly rare, but multiplied together, exactly the way the 6 spinning dials must all align at once to open that lock, the combined probability collapses towards something close to zero. Not because any single barrier is absolute on its own, but because the universe requires every single one of them to be cleared simultaneously by 2 civilizations that have never met, never coordinated, and have no way of knowing whether the other is even attempting the same thing at the same time. This is why the picture painted throughout this entire story is not simply one obstacle that a sufficiently advanced civilization might eventually overcome with enough patience or ingenuity. It is a compounding structure, one barrier layered directly on top of another, each one independently sufficient to prevent contact, and together forming odds so vanishingly small that even a galaxy containing many active civilizations across its entire 13-billion-year history may never produce a single successful physical meeting between any 2 of them. It is worth pausing on how strange this makes our own moment feel from the inside. Everything humanity has ever built, every language ever spoken, every war fought, every book written, every star ever mapped by naked eye or telescope, has taken place within a window of time so brief that it barely registers against the timescales this entire story has been describing. Written history itself stretches back only a few thousand years, a single flicker compared to the billions of years it took for this planet's chemistry to slowly climb from simple molecules to a species capable of writing anything down at all. Radio technology, the very thing that would allow us to send or receive any signal across interstellar distances at all, has existed for only a little over a century. A span so short that if the story of life on Earth were compressed into a single day, this entire chapter of human technological capability would occupy less than the final blink of the final second before midnight. And yet within that impossibly brief window, we have already mapped thousands of planets orbiting other stars, detected the faint afterglow of the universe's earliest moments, and built instruments precise enough to measure the almost imperceptibly small stretching of space itself. That is not a small achievement. It is, if anything, a sign of exactly how quickly a technological civilization can move once it gains the tools to look outward, which makes the brevity of our own history less of a limitation and more of a reminder that whatever else might be out there, assuming it exists at all, may be moving through its own version of this exact same brief, urgent window right now, unaware of us in precisely the same way we remain unaware of it. Both of us reaching outward during a moment so short that the odds of it lining up with anyone else's moment, anywhere else in the galaxy, remain vanishingly small, no matter how many civilizations actually exist. There is a strange kind of comfort hiding inside all of these numbers, if you are willing to sit with them for a moment, rather than only feeling their weight. Every barrier described so far, the crushing distances, the speed limit built into the fabric of space and time, the exponential cost of approaching it, the brief and poorly aligned windows during which any 2 civilizations might both exist, and the slow, permanent sealing off caused by the expansion of the universe itself, arises from the exact same physical laws that made your own existence possible in the first place. The same gravity that spreads galaxies across such enormous distances also gathered the very hydrogen and helium left over from the early universe into the first generation of stars that lived, burned, and eventually exploded, scattering the carbon, oxygen, and iron that would later become planets, oceans, and eventually the atoms inside your own body. The same nuclear physics that determines how long a star can burn, and therefore how long any world orbiting it might have to develop life, is the same physics currently keeping our own sun burning steadily enough to keep this planet warm and its oceans liquid. The same expansion of space that will one day seal off every other galaxy from view is the same expansion that, in the earliest fraction of a second after the universe began, stretched space just enough to allow matter to eventually cool, clump together, and form the very structures, galaxies, stars, and planets that everything else in this story depends on. Isolation and creation, in other words, are not two separate features of the universe working against each other. They are the same feature, viewed from two different angles. A universe built on a scale so large and governed by laws so precise that it can produce billions of habitable worlds and countless possible instances of life, while also, through those very same laws, keeping almost all of them apart from one another. It is tempting to view that combination as some kind of cruel design, a universe that builds life generously and then locks it away in isolation, almost as an afterthought. But it may be more accurate and more useful to see it simply as the natural consequence of a cosmos vast enough to contain everything discussed throughout this story at once. A cosmos that had to be exactly this large and exactly this old in order to have enough time and enough raw material to build stars, planets, chemistry, biology, and eventually a mind capable of understanding any of it, including a mind capable of sitting here, right now, working through exactly why that same vastness keeps it from ever meeting whatever else it may have built somewhere else entirely. There is one final way to hold everything this story has laid out, and it has nothing to do with distance, energy, or the mathematics of overlapping timelines. From far enough away, seen from the vantage point of another civilization's telescope, our own planet would appear as nothing more than a single, pale point of light, lost in the glare of its own star, indistinguishable at that distance from countless other points of light scattered across the same patch of sky. Nothing about that faint point would reveal the oceans, the mountain ranges, the billions of years of slow chemical experimentation, or the countless individual lives that have unfolded across its surface, each one convinced, in its own quiet way, of its own importance. And yet everything discussed throughout this entire story, every barrier, every equation, every failed and successful search, was carried out by minds living on that single, easily overlooked point of light, reaching outward across gulfs so vast that the reaching itself, however unlikely to ever be answered, stands as one of the more remarkable things the universe has produced so far. If somewhere else, on some other equally faint and easily overlooked point of light, another mind is doing the exact same thing right now, running its own version of these same calculations, reaching the exact same uncomfortable conclusion about the odds of ever finding company among the stars, then in a strange and quiet way, the two of you are already connected, not through any signal or vessel, but through the simple, shared fact of having arisen from the same universe, governed by the same laws, and having independently discovered the same difficult truth about how alone that universe tends to keep the things it creates. That kind of connection asks for nothing in return. It does not require a signal to ever arrive, a vessel to ever complete its journey, or a single word to ever actually pass between two civilizations separated by thousands of light years and thousands of years of mismatched history. It only requires that somewhere, at some point, the universe managed to produce more than one mind capable of looking outward and wondering, and that fact alone, quietly and without any need for confirmation, may be the closest thing to company that the structure of this universe was ever going to allow. This resolves an old and uncomfortable question in a quieter way than most people expect. The question was never really about whether anyone else is out there. The mathematics practically demand that somewhere across a galaxy holding 400 billion stars, and across 2 trillion galaxies beyond it, life has arisen many times over. And intelligence very likely has too. The real misunderstanding was assuming that existence and accessibility are the same thing. They are not. The universe appears to be extraordinarily generous with life and extraordinarily strict about contact, and both of those facts come from the exact same set of physical laws. The same expansion that once allowed the early universe to cool enough for atoms and eventually stars to form is the same expansion that now permanently isolates most of the cosmos from every other part of it. The same vast distances that keep civilizations apart also make it far less likely that a single catastrophe could ever wipe out every living world in the galaxy at once. The same slow stellar lifespans that create mismatched habitable windows are also what give any single world the billions of stable years it needs for life to climb, from simple chemistry all the way to a mind capable of understanding any of this in the first place. Isolation, seen this way, is not a flaw in the design of the universe. It is a natural consequence of a cosmos built on a scale large enough and old enough to produce complexity and awareness scattered so widely that no single event, no single silence could ever erase it all at once. There is something worth sitting with in that thought. Every star overhead is a sun, and many of those suns almost certainly warm worlds of their own, some of which may hold oceans, atmospheres, perhaps even minds looking back out at a sky just as unfamiliar to them as theirs would be to us. The light reaching your eyes tonight from some of those stars set out on its journey long before you were born, carrying no message, no greeting, only the simple fact of its own existence. You will very likely never meet whatever else is out there. But you and it were built from the same elements, forged in the same kind of stellar furnaces, governed by the same laws that made stars, planets, and thinking creatures possible in the first place. That is not the same thing as being alone. It is something closer to belonging to a universe so vast that no single point within it will ever see the whole of it, and finding that even a single, isolated view of it is still worth everything it took to have one. If this kind of question keeps you looking up at the night sky a little longer than usual, be sure to like this video and subscribe for more journeys into the cosmos. Take a moment, look up, and remember that the same silence separating every civilization in the universe is the same silence that once made room for all of them to exist at all.